All right, we're looking at another L'Hopital's rule question here. It's in the L'Hopital's rule section in the Stewart calculus book, section 4.4, number 19. Notice I didn't quite finish writing L'Hopital's rule. I wrote psych. I don't know, do kids still say that? That was when I was a kid in the 90s. We definitely said that. Anyway, let's look, because here's the thing. You don't always want to just assume you're going to use L'Hopital's rule on a limit, even in the section on L'Hopital's rule, because they might just throw something at you to mess with you. So the first thing you're checking to see if you can use L'Hopital's rule is you're doing a direct substitution, plugging in for the x values, and seeing if you in fact get the indeterminate form 0 over 0 or infinity over infinity, plus or minus on those from that direct substitution. And in this case, you don't. If you're thinking about L'Hopital's rule, and you're not quite sure, maybe you should write those limits separately, the numerator and the denominator. It's certainly you want to do that if you're going to do L'Hopital's rule as a justification for using it. Or, right is of the indeterminate form 0 over 0 or whatever it might be. In this case, though, the limit as x approaches 0 from the right of natural log of x. It's not 0. If you picture the natural log of x, parent function, that's what this is, right? Y equals natural log of x. It looks like that. It's got a vertical asymptote at x equals 0. And so as x approaches 0 from the right, that function is approaching negative infinity. So that's what that limit is. I was going to say that's the value of that limit, but infinity is not really a value. It's kind of odd even to write something like equals negative infinity, because nothing can equal infinity or negative infinity, right? In the context of limits, though, we can say this, and it's an accepted convention in math. This also implies that this limit does not exist, right? And it doesn't exist, but saying it equals negative infinity also tells us that it doesn't exist because it's diverging in the negative direction, that it grows in the negative direction without bound, right? But that doesn't mean that this limit doesn't exist, right? That doesn't mean that, because we could have a negative infinity over negative infinity or a positive infinity situation, which is an indeterminate form, and then it could be negative infinity in that case, or it could be positive infinity, or it could be 0, or it could be like 17.3 or negative square root of 3 pi, or who knows? It could be anything when you get an indeterminate form. So that's what we need to discover. So to do that, we just need to plug the bottom in too. The limit as x approaches 0 from the right of x. And when you do plug 0 in for that, well, you just get 0. And hey, that's not plus or minus infinity over plus or minus infinity. And it's not 0 over 0. This is minus infinity over 0, which is not one of the indeterminate forms listed for being able to use L'Hopital's rule. But more than that, it's not actually an indeterminate form. Infinity over 0, or plus or minus, whatever, is not an indeterminate form. And if you know what the answer to this is already, that's fine. Maybe you can skip this. I'm going to talk for a second about why it's not an indeterminate form. At the end, I will show an answer. So if you want to just kind of skip toward the end, if you feel like you got it, that's fine. But I want to talk briefly about what's happening here. There's kind of two things happening here, both of which would give a similar result, and we're put them together, and they just kind of accentuate that result, if that makes sense. So here, we're going to kind of put that note off to the side here. And here's the deal. On the one hand, if you take something over 0 or something close to 0, in this case, because it's a limit. And by the way, it would be helpful. As x approaches 0 from the right, x does approach 0, right? I'm going to go ahead and put a little plus up here too for from the right. Let me make that a little better. And it's it's a little informal to do that here. It's obviously part of the notation down here. Putting it up here, I think, is informal, but it's useful because it helps you remember. This 0 is a I'm doing air quotes here, a positive 0, right? It's not. When we're talking limits, we're not talking like the limit is 0, period. But we're talking about x values near 0, to the right of 0. So what we're approaching is 0, but we're approaching 0, right? The limit's 0 because we're approaching 0. And so we're actually at these y values, then the output of this, that are also positive values because y is just x. And so, if x equals like 0.00001, y is also 0.00001. So those values are all positive we're approaching 0 from the right. We're talking about a little to the right of 0, basically 0, but positive. So really quick, if you had like a result from a limit and you were getting like 7 over 0 from the right, right? So like a positive. What kind of an answer is that, right? If you get this from direct substitution. Here, let me write this down. And you would never want to write equals. Well, actually, if you write equals this, it's probably okay, because I'll tell you in a minute. Think about it. You have a number like 7 or whatever. It could be a million. It could even be like 0.001. But if this number is static, if this is a fixed number, and we're divided by something that's approaching 0, then what you have is like some fixed number divided by something that's getting tinier and tinier and tinier. And then, I don't know, maybe there's a 1 at the end or something, right? That's huge, right? Like the smaller this is, the bigger the whole thing is, right? If you take something finite and you divide it by something infinitesimal, right? Something teeny tiny. Then you get something huge. Something infinite, right? If you take a number like 7, maybe it's 7 cookies, right? And you divide them into teeny tiny infinitesimal little morsels, little crumbs, so small that they're like, we're talking subatomic particles here. They're not even cookie pieces anymore. They're just little bits of nothing. I don't know. Imagine that you could divide them infinitely small, which, obviously atomic theory gets in the way there, but whatever. How many would you have? Well, you'd have infinitely many if the pieces are infinitely small. That's the idea. Okay, so that gives you infinity as an answer, right? On the other hand, if you take, what if you just had a number on the bottom, like 7 on the bottom, and on the top you had, I don't know, let's say negative infinity, something that's growing without bound. This is also infinite. It's negative, right? But infinite magnitude, right? There's no limit to how big in magnitude this gets because the top has no limit. The bottom does. The bottom is just 7 or 2 or 0.1 or whatever it might be, right? But the top is this infinitely large magnitude. It's growing infinitely larger. That's like the result from direct substitution. Either one of these scenarios gives us infinite magnitude. This one would be negative. This one, as written, would be positive. But the point is they're infinite magnitude. So if you put those two things together, it's even more so. If you have something that's approaching infinite magnitude on the top and something that's approaching the infinitesimal on the bottom, super duper big, super duper bigly huge, right? This is the infinite magnitude on top. And you have something super duper duper tiny, right? Infinitesimal. How tiny? Like tinier than Ant-Man in the quantum space tiny. All right, super duper tiny, infinitesimal. That's what that word means. There's no limit to how small in magnitude. It's as small as it needs to be and then some, right? If you take super big divided by super tiny, of course it's going to be infinite in magnitude. The whole thing is going to be like super infinite, right? It's just infinity. It's infinite magnitude. We don't want to make too many generalizations about exactly how big of an infinity it is. That's a whole different conversation. But yeah, all right. So infinite magnitude. So that's what we're dealing with here. Anytime you get infinity over 0, that is not an indeterminate form. It's not at all indeterminate. Indeterminate means when you get it, you don't know what it is when you get that from a limit, right? There's like ambiguity in there, right? The numerator and denominator of a fraction are both doing the same kind of weird thing. Like they're both approaching 0, or they're both approaching infinity or negative infinity, or one infinity and a negative infinity, right? Or something approaching 1 to something approaching infinite power, something where the two things are in tension in a way that it's hard to tell who wins. This is not that. This is something super strong beating up on something super weak. And so the decision is not in doubt. The decision is an infinite result. And since the numerator is negative and the denominator is positive, it's going to be negative. And so the answer here, I know I talked for a long time. You don't have to talk that long or think that long to answer this question. If you know what to do, it's just negative infinity is the correct answer here. But I wanted to get at the core of what this problem means. So this is the answer. And yeah, it's in the section under L'Hopital's rule as a red herring because it kind of looks like it, right? There's a lot of problems that look like this in there. If this was x approaches infinity, then it would be a L'Hopital's rule problem. And there are some problems in the book like that. But because you don't get one of those forms, you want to look closer and think, okay, is this even an indeterminate form? And it's not. By the way, when we say that a limit equals negative infinity, I mentioned this before, it also means that this limit does not exist. You don't necessarily have to write that. Saying that a limit equals negative infinity also implies that it does not exist. That's what that means. But it's more specific to say that it equals negative infinity because it tells you that the value of this grows without bound in the negative direction as x approaches 0 from the right. In other words, this function has a vertical asymptote at x equals 0, and it's approaching it by going down to negative infinity as x approaches 0 from the right side. That's what that says.